So this time, let's talk about 6 trigonometric functions of our 45-degree angle. Now, when I developed the 60-degree and the 30-degree angle triangles, we were dealing with an equilateral triangle that we divided in half. For a 45-degree triangle, we're going to now deal with a 45-degree, well, trigonometric function here, where we're going to have 45 degrees, right? So we're going to deal with a square. Each side of the square is equal. So let's just pick a number here. Let's make it equal to 1 here, right? So let's say you've got each side having a length of 1, right? Now, if I take each side of this right triangle right here, or this square, and I divide it in half to make a right triangle, I can divide it in half by just chopping it down the corner, corner to corner right here to make a diagonal. And so if I do that, what happens? Well, sure enough, I get a right triangle. Now, what about the length of the hypotenuse of that right triangle? If we use our Pythagorean theorem, we know that the following will happen. A squared plus b squared must equal c squared. I'm sure you guys probably already know the answer to this one, but I'm going to go through it anyways. 1 squared plus 1 squared is equal to c squared. So the square of the length of the hypotenuse is 2, making our hypotenuse have a square root of 2 length. So now every single time that I'm dealing with a 45-degree right triangle, I can think 1 square root of 2 as the lengths of my sides right here. Don't forget, we also will want to be able to deal with this in terms of radians, so we might as well go ahead and do the conversion. What happens if we take 45 degrees and convert that into radians? Well, we take pi divided by 180 and multiply it by 45 degrees in order to do the conversion, and we find that we are going to get, well, 45 and 180 are both divisible by, well, 45 in fact, right? Because 45 divided by 45 is 1 times pi. The denominator, 180 divided by 45, ends up being 4. Well, actually, that should make sense, right? Because if you think about it, 180, if you divide by 2, gives you 90. And of course, 90 divided by 2 again would have to be 45. And therefore, 180 divided by 45 would give us 4. Okay, so that means that if we have our right triangle expressed in terms of radians, here it is, that's it. So, what could we say? The sine of the angle 45 degrees, which is the same as saying the sine of the angle pi over 4, and I'll just go ahead and put this all in one line for this particular function, for our basic ones, is always going to be 1 over the square root of 2, but we rationalize that and express it as square root of 2 divided by 2. For the cosine of 45 degrees, also known as the cosine of pi over 4, radians, right? We don't write radians, we just put the number after it. We're also going to get square root of 2 over 2. And the tangent of our 45-degree angles, which is to say the tangent of the angle pi over 4, if we take the opposite over the adjacent, opposite over adjacent, we get 1 each time. All right, similar stories for each of the other ones here, but let's just run through it. So you see, if we take the cosecant of our 45-degree angle, we're going to get square root of 2 over 1, or just square root of 2. It's hypotenuse over opposite. If we take the secant of 45 degrees, we also get square root of 2. And if we take the cotangent of 45 degrees, we get 1 yet again. Okay, so all of these are repeated for our radians, right? We should know each of these measurements one by one for all of our special triangles from 30, 45 to 60 degrees. because we'll end up using them quite a bit. Okay, more to come.